Hi, it's Miss Austin, and I'm going to be going over the Unit 2, Lesson 17 practice problems. We're doing numbers 1 through 3 and 5 through 7, and these start on page 191 in your book. So number 1, Jada is planning a kayak trip. She finds an expression for the time, T of S, in hours. It takes her to paddle 10 kilometers upstream in terms of S, the speed of the current, in kilometers per hour. This is the graph Jada gets if she allows S to take on any value between 0 and 7.5. So we can see here from 0 to 7.5. What would be a more appropriate domain for Jada to use instead? Well, since this is a real life problem, and we can tell that this is the picture of a rational function, this branch over here really doesn't make any sense in a real life setting. So really, we only want to look at this part of the graph. So it would be more appropriate to maybe go from 0 all the way anywhere between like 4.5 and to 5. So I would say let's let speed be anything from 0 to 5. So we're only considering those solutions. Okay. B, what is the appropriate speed of the current if her trip takes 6 hours? So this is speed. And then Y is the time. So they're telling me it takes 6 hours. Here's 6. I'm going to follow this over to the graph. About right there. So if I look down here, what is that? So we're going to have to approximate, I don't know, 3.8, 3.9, 3.8 kilometers per hour. If the speed of the current is 3.8 kilometers per hour, the trip is going to take her 6 hours. All right, number 2. A cylindrical can needs to have a volume of 6 cubic inches. A label is to go around the side of the can. The function S of R equals 12 over R gives the area of the label in square inches, where R is the radius of the can in inches. So they want to make sure we understand what happens when we divide by increasingly smaller and smaller numbers and increasingly larger and larger numbers. So the first question says, as R gets closer and closer to 0, so when I put smaller and smaller numbers in for R, what's going to happen to this value? It's going to get larger and larger. And you could convince yourself, you could take 12 divided by 0.1, 12 divided by 0.01, 12 divided by 0.001. And you could convince yourself that this is true. Okay, so as R gets closer and closer to 0, the area gets larger and larger. As R gets larger and larger, what does the end behavior of the function tell you about this situation? So as I continue to put larger and larger numbers in here, what's going to happen? It's going to get closer and closer to 0. And you could convince yourself, again, with a calculator, you could take 12 divided by 100, 12 divided by 1,000, 12 divided by 10,000, and you're going to see that, right? If you can imagine a picture of it. And you could go to Desmos and look at this as well, right? As R gets larger and larger and larger, this answer down here is going to get closer and closer to 0. And then the reverse was true over here. As I put smaller and smaller numbers in for R that are close to 0, the answer is getting larger and larger. Okay, so when I put larger numbers in for R, the end behavior tells me the answer is getting closer and closer to 0. The area is getting closer and closer to 0. Okay. Question number 3. What is the equation of the vertical asymptote for the graph of the rational function g of x equals 6 over x minus 1? So today we learned that rational functions have what are called vertical asymptotes, and those occur at whatever makes the denominator equal to 0. So when I think about this x minus 1, what number is going to create 0 there? X equals 1. So if you were to graph this on Desmos, you're going to have one branch over here. I'm just sketching this very quickly, and one branch over here. This line, which we write as a vertical equation, x equals 1. And how did I figure that out? It's whatever number makes that denominator equal to 0. So that's A. We are skipping number 4. That is from a lesson that we did not do in Unit 1. Number 5, review question from our work with polynomials. Is this the graph of g of x or h of x? Explain how you know. So first of all, I would, maybe for whatever reason, my eyes are checking the zeros first, right? They both have x squared, which means they touch at 0, and they bounce there because they have a multiplicity of 2, and then they both say x minus 2. So okay, that's good. So the only difference is this one has a negative in it in the front, right? So overall, this is a third degree. They're both third degree, but this one has a negative in front and this one has a positive. So which is right? Well, if you remember from our work with polynomials, if you have an odd degree with a negative leading coefficient, then the end behavior is exactly what this picture is. As x gets larger and larger in the negative direction, y gets larger and larger in the positive direction. As x gets larger and larger in the positive direction, y gets larger and larger in the negative. So how did I know this was right? I mean, you could go to Desmos, but I knew because it had a negative leading coefficient and an odd degree. So I knew that this was the correct end behavior. So g of x is the right one. Okay. Number 6. Now, a 6-ounce cylindrical can of tomato paste needs to have a volume of 178. The current can uses a radius of 2.75 and a height of 7.5 centimeters. Use graphing technology to find a cylindrical design that would have less surface area, so each can uses less metal. And instead of graphing, technology, I'm just going to use my calculator. I'm going to use the formula, right? The formula from our work in lesson 16 was the surface area for a can is 2 times pi times the radius squared. And if I knew the volume and I rewrote the height based on the volume, we ended up with this. Whatever the volume is, it's that number doubled. So 178 times 2 is 356 over R. And you can go back and look at your work from lesson 16 or the lesson summary to see how we got that. But hopefully that's starting to emerge as a pattern to you. So right now, let's figure out what the surface area is with this radius. So I'm just going to go to my calculator and I'm going to plug 2.75 right there. So I've got, maybe this light is, 2 times pi times 2.75 squared. There we go. Plus 356 divided by 2.75. I'm trying to figure out what the surface area is right now. So with the current radius and height, the volume or the surface area is 176.97 square centimeters. I'm trying to find less. I want to save the company money. So I want to make the can that can still hold 178 cubic centimeters, but I want it to have a smaller surface area. So if you remember our work in this lesson, well, what are we going to do? I don't know. I could try a little higher or a little lower. I'm going to go for 3. Let's try 3. So as is, that was the surface area. So now I'm going to try 3 for the radius. So now I'm just going to go to my calculator. I'm going to take 3 and I'm going to plug it in right here and right here. And I'm going to see if I can get a number less than that. So here we go. 2 pi times 3 squared plus 356 divided by 3. Look at that luck. 175.2. So a radius of 3 gets me a surface area of 175.22 centimeters squared. So radius would be 3. Now, if they wanted me to figure out what the height of the can was, okay, I could go back, and in our work in lesson 16, the height was the volume divided by pi times the radius squared. Well, we're saying 3. So I'm just going to type that into my calculator so I can give the company all the dimensions that they need. Pi times 9. I'm putting that into the height is about 6.3. And these are not the only answers. I mean, maybe 2 point, instead of 2.75, maybe 2.9 is smaller. Maybe below 2.75, maybe 2.5. We don't know. But I did find this example right here that does produce a smaller surface area. All right, last question. The surface area S of R in square units of a cylinder with a volume of 20 cubic units is a function of its radius R in units, where S of R is equal to 2 pi R squared plus 40 over R. So there's that equation again, right? Now look, see when the volume is 20, it ends up being double the volume over the radius. I'm hoping you're starting to see that as a pattern. What is the surface area of a cylinder with a volume of 20 cubic units? So we're using this volume, which means this formula will work, and a radius of 4. All we have to do is plug 4 in and do the math. So we're going to go 2 times pi times 4 squared plus 40 over R. And we could leave the answer in terms of pi, right? So that would be what? 16 times 2, 32 pi plus, whoops, I forgot to plug 4 in there, plus 10. And I didn't write 2. Come on, Miss Austin, get it together. 32 pi plus 10. Or I could actually get the value. 2 pi times 4 squared plus 40 divided by 4. Surface area is 110.53 cubic units. So this is just written exact, right? Because pi, we're just leaving it in terms of pi, but if you type it in the calculator, you get 110.53 cubic units. All right, I hope this was helpful, and I will see you soon.